Hello. We're going to talk a little bit about the tangent problem. So this assumes that you've already done some work on the velocity problem, where we were using average velocities to approach instantaneous velocities. And when we graphed that, the average velocities were those secant lines on the position versus time graph. And as we moved that time to be closer, the time interval, I guess, to be smaller, then that approached the tangent line to a specific instant on the position versus time graph. And as it turns out, we can generalize this. It doesn't have to be a position versus time graph. It doesn't have to be interpreted as a velocity. You can take any function and talk about tangent lines and use this process to find the slope of the tangent line. So let's make sure first that we know exactly what we mean when we say a tangent line. So a tangent line to a point on the curve P is a line that touches the curve at point P and only at point P in that area. And then it also matches the curve's slope at point P. And so there's a good example down here to illustrate what we mean by that. You've got a point P here, and here's its tangent line, and you can see that at this point of the curve, the curve is starting to go uphill, so its slope would be considered positive, but not a huge number. It's not real steep. And so its tangent line also has that small positive slope. If we look at the next picture, you've got the same idea in this tangent line here. It's tangent at this point because if we look at the slope, it's touching the curve at that one point, and the curve itself is starting to go downhill. So we would expect its tangent line, if it had the same slope, to be a slightly negative sloped line. But if you look at this other place here, this line continues and intersects the curve again in this spot. But if you look at what's happening to the curve in this spot, it's starting to go uphill, similar to what we had in this first picture. But this line has a downhill slope. And so this is not considered a tangent line because it is not matching the curved slope at that point. So that is just some clarification on a tangent line. And what we're going to work on doing is finding the slope of the tangent line. But as you know, in order to find the slope of a line, you need 2 points. And if we're looking at a tangent, you would only know 1 point. You would know that point of tangency, its x and y coordinate, but you don't know any of the points that are elsewhere on that tangent line. So you can't actually find the slope using the traditional slope formula in the way that we've done before. So what we're going to do is similar to our velocity problem is we're going to use secant lines. We're going to take another point on the graph and we'll calculate the secant line, the slope, I guess, of the secant line through those 2 points. And then we'll move that second point closer and closer till it becomes really, really close to that point of tangency. And that becomes closer and closer to the actual tangent line. So there's an animation link here, and I just wanted to show it to you. Let's make sure. Okay. Here's a picture of a curve. You can see over on the left side that this curve happens to be e to the x, but you can play around with this and put in any function you want, sine x, x squared, etc. And in this situation, we have the slider, the first point here is going to be our point of tangency. And so I had it at 0. Sometimes there it is. It's at 0. So we're going to try to approximate the slope of the tangent line there. And the way we do this is by taking this second point. You can make it start wherever you want, but moving it closer and closer. And watch that secant line. It becomes closer and closer to becoming an actual tangent line at that one point. And of course, you could move it really close and even closer, and you can even put in values for how far away you want it. And that secant line is now very, very closely approximating the tangent line at that point x equals 0. So that's kind of the process we'll be using. And let's talk a little bit about some notation. If P and Q are the 2 points on the curve, then we're going to note the slope of the secant line by this M sub PQ. Okay. And as Q gets closer to P, we say that Q approaches P. That's the lingo. And we write that with an arrow notation. Q approaches P. And as Q approaches P, the slope of the secant line approaches the slope of the tangent line. I'm just going to write tan line at P. And so that means that what we're introducing is this idea of a limit. We say that the limit of the slopes of the secant lines is the slope of the tangent line. And we write it with this notation. LIM, and underneath that, we indicate what's approaching what. So the limit as Q approaches P, and then of those secant line slopes, which we denote with M sub PQ, equals the slope of the tangent line, which will be M sub P. So that's just introducing that limit notation. We're going to do a lot more with it in a later section, but just getting an idea of what it's going to look like when we get there. So in the meantime, we'll do one quick example. We're going to start with this function f of x equals 1 over x here. It's graphed here in the first and third quadrants. And we're going to work on trying to find the slope of the tangent line to this point P. And the coordinates of P are 1, 1. So this point has these coordinates, which is in fact on that line. If you plug in x equals 1, 1 over 1 is still 1. So there's our point on the curve. And what we're going to do is we're going to come up with just some Q values, some of them that will be over here on the left side of P, and calculate the slope of those secant lines, and then some Q values over here on the right side of P, and calculate the slope of those secant lines. So I have some space to do that here. Let's make sure we understand what we're being asked to do. So we're trying to find the slopes of the secant lines to the curve with the following x values of Q. So what this is telling me is that this is the x value of the Q point, the point that's not the point of tangency. So I'm going to need, in order to find the slope of a line that contains that point, I'm going to need to find the y value. Remember, the function we're working with is 1 over x. And so to find the y value, I need to plug in the x 0.9 into the 1 over x function. So hopefully you got a calculator handy. 1 divided by 0.9, and I get 1.1 repeating. I'll just use 3 decimal places for the sake of this example. And so now I have my Q point. Remember, our P is right here. This point is not changing for the entire problem. That is the point of tangency. And so what I need to do is I need to calculate the slope of the secant line that goes through the P and the Q in this particular box. So I'll do y minus y over x minus x. And again, plug that into my calculator. And I get negative 1.111. Okay. So I have taken my first Q, which is slightly to the left of P on the graph because its x value is a little bit smaller, and I've calculated the slope of that secant line. So let me set up the next one. I'm going to do the same thing in part B, but now my Q point has a slightly closer x value. It's even closer to p. It's 0.99. And so I need its y value. Remember, I'm going to plug that into the function 1 over x. So 1 divided by 0.99. I get 1.0101. So that's repeating. And I'm going to do the same calculation. I'm now going to find the slope of the tangent, secant line through that new q and the original p. I think I switched my, sorry about that. I just realized when I was checking over, I used my qy value first. So I need to use my qy value, my qx value first as well. And I switched those, which is why when I put it in my calculator, it didn't come out negative, and I figured I just missed something, and now I realize what I missed. So I apologize. Here I started with q values, so it needs to be q values first for both x and y, and so same thing here on my second example. Okay, so if I'm going to plug those in, I get negative 1.01. Okay, so we have 4 more of these calculations to do, where we need to first figure out the y value for your q, and then calculate the slope of the secant line with that q and the original p. So I'm going to encourage you to go ahead and pause the video while you do those calculations to make sure you're comfortable with them, and then I will also do them at the same time, and they'll magically appear. Okay, so I've gone through, I've done those calculations, and I have slopes for all of 6 of my secant lines. We take a minute to just look at what we have. In A, B, and C, you'll notice that all those q values are just slightly less than 1. So those would be representing points that are on this side of P. And when we did that, we saw that the closer we got to that P point, because each one of these x values is getting closer and closer to x equals 1, my y values, or I'm sorry, my slopes got closer and closer to -1. And then we notice the same thing for D, E, and F. These x values are on the right side of P in our picture. They're slightly bigger than x equals 1. And as we get closer each time, our slopes of our secant lines are also getting closer and closer and closer to -1. So from these calculations, we're going to go ahead and estimate the value of the slope of the tangent line at P, MP, to be -1. I'm using approximate instead of equals because that's what we're doing. We're using a table of data points that are close to make an educated guess at what that would be. And it told me to sketch that line. So let's see here if I've got a good line tool. I can try to kind of get that line right in there. So there's a picture of that tangent line at P. Okay, so that you can see that that's actually very similar to what we did when we were calculating average velocities and using them to estimate an instantaneous velocity. The velocity and the tangent problems are really, really very similar. And hopefully that gives you kind of this intuitive sense also of what a limit is. A limit is kind of a value that all these other calculations are getting closer and closer to. And it is, in fact, this limit process and what a limit truly is that defines what calculus is. Everything we do is going to be based on limits. So hopefully you now have an intuitive sense of what those limits are, and we'll be doing more with them as in future lessons.